Okay, yeah. So today I'm going to talk about the interface of machine learning and dynamical systems. It's more of a survey-like style. So there's a lot of material. It's something that I've been working on for about a bit more than 15 years. I understand that we have about 45 minutes today. So yeah, feel free to give me like 5 minutes sharp before the end. So this don't work with many people that are listed here. So the general context of my research is how to analyze complex systems. So I tackled the different approaches in my work, but here in this talk I'm going to focus on two known approaches, which are the theory of dynamical systems and machine learning. So the theory of dynamical systems is a classical theory that allows to analyze complex systems when the model is known. So it has been formalized by people like Poincaré and Lyapunov in the late 1800s. So it offers non-trivial ways to analyze dynamical systems, and it has the status of theory, but it is currently limited to low-dimensional models. On the other side, machine learning is very popular nowadays. It's concerned with algorithms designed to accomplish a certain task whose performance improves with the input of more data. It allows the analysis of some very high-dimensional complex systems on the basis of data when the model is not even known. But it's mostly a set of techniques and algorithms. There are like no clear methodologies, and the theory is still underdeveloped. So it's mostly a set of different techniques and algorithms. So there is a lack of unity in a way. So it's not clear why certain methods work and what is their domain of applicability. So it makes sense from this point of view is to combine machine learning and dynamical systems in the following directions. So the first direction is machine learning for dynamical systems, where the goal is to analyze dynamical systems on the basis of observed data rather than attempt to study them analytically. So here, our goal is to extend the boundaries of the classical theory of dynamical systems. So it will be still within the framework of the theory of dynamical systems, but by expanding it towards the cases where machine learning showed that the method works. And the other direction is dynamical systems for machine learning, where the goal here is to analyze algorithms of machine learning using tools from the theory of dynamical systems. So here we would look at algorithms as dynamical systems themselves, where the time here is time on the computer and not necessarily time in the clock. And so this would allow to identify the domain of applicability of the algorithm in machine learning. And so this is something that was pointed out by Steve Smale in the introduction of the following book. I was discussing about this book with Omar a few minutes ago, where he said about like almost 20 years ago that the unification of dynamical systems and learning theory is a major problem, and that another problem is to develop a comparative study of useful algorithms currently available and to give them unity. And that's actually how I started my journey in this interface through the encouragement of Steve Smale around 2008, where I was working with Jake Bouvry, who is doing a postdoc with Steve Smale. And then this is what, for example, in our second paper on this interface of machine learning and dynamical systems, we said that it's easier to compute, to simulate a dynamical system than analyze the empirical data rather than attempt to study them analytically. But the mathematical theory necessary to analyze dynamical systems on the basis of observed data is still largely underdeveloped. So the hard work here is mostly to work on this interface between the two. So I'll talk a little bit about kernel methods and then and their applications. And then I'll talk about how to use kernel methods to learn dynamical systems and also to analyze dynamical systems. But when we're dealing with dynamical systems, I mean, it's not necessary always to just learn the dynamical system and then analyze the approximation to get results about the original system. You can do it the other way around, where you can have a database analysis. So here the goal is really to have a database theory of dynamical systems instead of approximating the dynamical system and then analyzing the approximation. So that's sort of a philosophical point of view where a lot of people, for example, they work on approximating the right-hand side of the differential equation and then analyzing the approximation. Here we want to argue that, well, it's not necessarily the best track. The best track is to try to take the theory of dynamical system and then make a database version of it. And that is what we did here, for example, where we have a database version of the center manifold theorem, a database version of constructing Lyapunov functions, where we show that the constructed Lyapunov function is also a Lyapunov function for the original system. Also here, for example, database version of solving the Hamilton-Jacobi-Bellman equation, and also database version of model reduction, where you don't necessarily approximate, you just approximate the quantities that appear in the theory. And the approach is that the way we are going to look at it here is that we are going to assume that there is a mapping that takes us from Rn into some Hilbert space that maps the ambient variable into some variable z. And then the goal here of this Hilbert space is to make computations simpler. So it doesn't necessarily mean that it's a linear analysis or that the system becomes linear. It's the key is to simplify computations when we work in this Hilbert space. So here, like a common comment that I always have is that, okay, what's the link between this and Koopmanism? So Koopman, they assume that the system becomes linear in a higher or possibly infinite dimensional system. Here we are saying that we are applying linear methods without necessarily assuming that the system is linear. And then it doesn't have to be always like linear method. It can be simply a method where computations become simpler. And the phi is obtained from the kernel that defines the Hilbert space that is called RKHS, which is a reproducing kernel Hilbert space. And so we are constructing a Hilbert space from data. So the data that we get allows us to construct a Hilbert space where computations become simpler. So that's the philosophical framework for this approach. So what is the context? That appeared in the 30s as an answer to the question, when is it possible to embed a metric space into a Hilbert space? And so the historical context is that in the 30s, people had complex problems, but they did not have the computational power. And in particular, for example, quantum mechanics, people had also like a lot of complex problems. And I think it has like the flavor of quantum mechanics because the goal is to construct a Hilbert space from data. And so what they had there is that, okay, we have complex problems. We don't have the computational power. So what can we do? And the trick was, okay, why don't we map complex problems into different spaces where the problem becomes simpler? And this is exactly what this question is asking, which is when is it possible to embed a metric space into a Hilbert space? Metric space is non-linear, Hilbert space is linear, and the idea is to try to find embedding results from one space to the other where things become simpler in the other space. And the answer there is that if the metric satisfies certain conditions, it is possible to embed the metric space into a special kind of Hilbert spaces that are called reproducing kernel Hilbert spaces. And since then, I mean, there have been a lot of work, especially through the work of Aronjan in the 50s, Schwarz in the 60s, Wahba in the 90s, and then they died here a little bit between the 60s and the 90s, but then they were resurrected by Wahba in the 90s, and then there have been a very active area since then, especially through the work of Wahba and Smail since the 2000s. So what are they? I mean, these spaces are, before anything else, they are Hilbert spaces, but with two extra properties. First property is the reproducing property, which is like you see that we have the evaluation functional. It can be written as an inner product. So these are very similar to what we know about Dirac functions, where if you have a function f, and then you want to evaluate it at a point, you can always write f of x as the integral of delta with the multiplied by f. But here delta is not like properly speaking a reproducing kernel, but it has the flavor of it. Second property is that the reproducing kernel has a span that is dense in H. And one of the properties is that the RKHS is unique, that we have symmetry, that we have positive definiteness according to that property here. And we have this decomposition that KXY can be written as an inner product in H. And if you remember the question that can we embed a metric space into a Hilbert space, which essentially means can we decompose the metric as write it as an inner product in H. And this is what led to defining the canonical feature map, which is Aron-Jan feature map, which is defined by this object here, PCX equal to KX dot. And in addition, if you add continuity, then we get Mercer kernel. And this is something that is important in the development of the work here. And yeah, examples of kernels that we have the monomial, Gaussian, hyperbolic tangent, and different other functions. Yeah, so RKHS, they play like an important role in learning theory, whose objective is to find an unknown function from random samples. So this is like in learning theory, what happens is that you optimize this functional, and then you can get a closed form of the best function. But then this depends on the unknown probability function, which is rho. So in practice, this leads to the following approximation of the empirical error with the regularizer that is belonging to the RKHS. And so the lambda here plays the role of the regularization parameter. So what happens here is that once you minimize that criterion, you are going to get fsx, I mean, the approximation to be equal to linear combination of the phi jx, which is Aron-Jan's feature map. So you already see linearity in the phi j's, and the cj's themselves, so they satisfy a system of linear equations. So we got the simplification happening for this simple problem of approximating an unknown function from random samples. In that context, learning is the process of approximation, the unknown function from random samples. Another application is the problem of change point detection, where our goal is that if we have a sequence of samples x1 to xn, we are looking for a possible change point tau, such that before tau, the points are following probability distribution p, and then after tau, we have the samples are following probability distribution q. And the approach here is still similar. You map the data set into a higher dimensional space, and then one computes a measure of discrepancy delta n. So if delta n is small, then p is equal to q, and if delta n is large, then p and q are far apart. So we'll be in this work, we'll be using the maximum mean discrepancy, which is the difference between the means in the RKHS. So basically what happens is that if you have probability measure p, so you compute what is called the kernel mean embedding, which is essentially computing the mean in the RKHS. And then if you want to compute the maximum mean discrepancy between two probability measures, p and q, then this will be the difference between the means in the RKHS. So you see also the flavor of linearity, because you are looking at just difference of means, but in a different space. And so this can be computed directly from data and through this expression here, but we'll see the other expression shortly. So one of its issues is that it's pseudometric on distributions, but it doesn't satisfy exactly the properties of the metric, but it becomes a metric if the kernel is characteristic, for example, the Gaussian kernel, both on compact domains and RD, for example. So this is what I was illustrating here, is that you have probability distribution P, you compute the kernel mean embedding, which is the mean in the RKHS, and then probability distribution Q, you map in the RKHS and you get another probability distribution, you get another mean, and then you compute the difference, and this will gives you a measure of discrepancy. And yeah, so as I said, so it's a metric. So it has the same flavor to what I mentioned before, is that you are not necessarily computing an estimate of the density and then computing the difference between the means of the estimates of the densities. What you are going to do here is that you are going to discretize the metric itself. So this is why one of the advantages is that you are computing the database version of the metric. So it's an integral probability metric that can be computed directly from data without having to estimate the density as an intermediate step. And this is like one of the formula that we'll be using in this work. And yeah, so okay, now let's look at the question of learning dynamical systems using kernels. And then we are going to look at how to choose the kernel. What is the best kernel in this sense? And so here we are going to discuss the method of kernel flows. So here the question is similar. So given input-output data, how to recover an unknown function u star so that u star xi is equal to yi. So this problem, in the setting of optimal recovery, this problem is ill-posed, but it can be turned into well-posed problem by restricting candidates for you to belong to a certain Banach space with the following norm, and viewing the optimal recovery as the minimizer of the following relative error. But essentially, this gives the following approach to learn the parameters of a kernel. So the method of kernel flows is based on the premise that a kernel is good if there is no significant loss in accuracy in the prediction error if the number of data points is halved. So here, halved is just something relatively subjective. So we explored this further in recent work where we argued that actually the underlying principle is compression in the sense of algorithmic information theory, that the kernel is good if we are able to apply Kolmogorov complexity and the minimum description length. But that's like another paper that I will not talk about today. So today I just want to focus on this principle that will say that the kernel is good if there is no significant loss in accuracy in the prediction error if we reduce the number of data points. And so in practice, what happens is that if you have a kernel parameterized by theta, for example, I think about the Gaussian, where you have are trying to learn the standard deviation, then you are going to get first, if you have take your data set, you select a random subset of size n, and then you select another subset of size n over 2 through randomization in both cases, in the first step and the second step. And then you compute this relative error, which is 1 minus. So y is the approximation with the capital N over 2 points. And then here you compute the matrix, which is k theta xc. And then you do the same thing in the denominator, which is the full data set of size capital N. And then you run gradient descent so over theta, and then you get theta k plus 1 is equal to theta k minus delta gradient rho of gradient rho with respect to theta. So it's like a learnable, like trainable machine learning method that is not necessarily a neural network, but there is definitely a link between neural networks and the kernel methods in this context. But at least here you see we are learning parameters of the kernel through this approach. So now we are going to apply it to learning dynamical systems. And so we assume that you have a time series, x1 to xn. And then our goal is to forecast xn plus 1 from the past. So here we recast the problem as trying to approximate f. So here I'm going to get zk plus 1 is equal to f dagger zk, and then get all the way to the past through a time delay. So here we'll talk about the case where we don't learn the time delay, but if you look at the paper, you see how to learn the time delay itself from data. So this problem here can be written as yk is equal to f dagger xk, where yk is the future, and xa is the past up to top. So this like reminds us of the previous discussion about approximating an unknown function from random samples. And here we already know what the closed form solution of this problem in the context of kernel methods. So this is given by the following closed form solution. As I said before, I mean, when we learn a dynamical system, it's not necessarily the same thing as learning an unknown function. So there is, we have to be aware of the difference between learning a function versus learning a dynamical system. So this led to introducing like different variants of kernel flows. So here, this is the first one, which is like quite close in spirit to learning an unknown function from random samples, and it's quantifying, like trying to have short-term prediction. So here we say that the kernel is good if the relative error between the short-term prediction when we have data doesn't change much. But then if we want to have other dynamical quantities, like for example, we want to go the long term, then in that case, I mean, it makes sense to use Lyapunov exponents And then here we have a version of regarding the maximum Lyapunov exponent, where we say the kernel is good if the estimate of the maximum Lyapunov exponent with capital N points versus N over 2 does not change much. So this is in a way characterizing the long-term behavior. So when you are learning dynamics, you can have like short-term, but you can also you also want to have long-term. You can also have statistical properties, like in the case of Frobenius Perron operator, where you want to see the evolution of the data through the dynamics. So if you start, if your initial condition, for example, satisfies some certain probability distribution, and you want to move it forward through the dynamics, then this is what the Frobenius Perron is telling you about. And then the idea would be how to characterize this push forward of the dynamics. And here we are conjecturing that here it makes sense to look at the following metric, which is the maximum mean discrepancy that we talked about. And the claim is that the kernel is good if the maximum mean discrepancy between two subsamples does not change much. So that's like in a way have a statistical contact of the dynamics. And then if we talk about attractors, then we can also look at, if we have a system with attractors, then we can say that in that case that the kernel is good if the Hausdorff distance between the reconstruction of the attractor with capital N points versus N over 2 points does not change much. So we have also like recently developed like another one with invariant sets for dynamical systems with not necessarily attractors, but with invariant sets. And then here we have it's like similar spirit to that one, but the only difference is that we had to modify the Hausdorff distance itself, because for invariant sets, when the classical Hausdorff distance doesn't necessarily work well. So okay, so we start with toy models. So we start, for example, with the simple kernel, so containing the Gaussian, Laplace, locally periodic. So here the goal, as I said, when we are learning the dynamical system, it's not necessarily about learning the right-hand side, but it's about like really learning the patterns or the qualitative behavior of the system. So this is why we had to add, for example, the locally periodic kernel in order to detect periodicity. So this one is for in case if there is a jump. This is the triangular kernel is for detecting these kind of jumps. This is for the long run, like the quadratic kernel is for the long-term behavior. And then Gaussian and Laplace is more for the local behaviors. In a way, so we are trying to balance things out, but qualitatively speaking. And we tried with one of the most important toy models in dynamics, which is the Bernoulli map. This is xk plus 1 is equal to 2xk mod 1. And then here what we notice, for example, in the case before learning the learning, so the true is the blue here. Before learning the kernel, you have the red. I mean, you don't have good approximation, but then on the left side, you have after the learning the kernel. And then for a different initial condition, blue is true, red is approximation after learning the kernel, and green is before learning the kernel. So you see this has like a learning the kernel definitely improves performance. And then we also dealt with the attractor case, like with Lorentz, the 3D system. So these are the errors. These are the time series for X, Y, Z. These are the errors. Red is after learning the kernel, and green is green is before learning the kernel. So these are the projections of the attractor in 2D. So first, third, and fifth are after learning the kernel. 2, 4, and 6 is before, and this is like the reconstruction in 3D. Left is after, and right is before learning the kernel. And then we applied this to a real data set. So after uploading this paper on the archive a few years ago, I mean, someone from Argonne National Lab contacted us about applying this to a true data set, and which is like climate modeling. And here, this is what, at Argonne National Lab, they had data from from the climate, like real data sets, and then they were using two PDE methods implemented on supercomputers. And then, so yes, I think it's visible here. Yeah, so here you see like the HiCom and CSM, they were taking like 800 core hours on their supercomputer, CSM 17 million core hours in this supercomputer. And then with LSTM, they had also this Theta supercomputer. It was taking a few hours of fall time. And then using our method, the blue one, with kernel flows, you see we are competitive. And then it took 40 seconds to train. And the kernel was not like as simple as the one I mentioned, but it has just slightly more parameters, about 20 or I forgot 21 parameters or so. So this is what you see for the short-term prediction. But if you remember in dynamics, as I said, we need to look at short-term versus long-term predictions. So this is, for example, the temperature profiles. This is the true temperature profile. And then this is with our approach, kernel flows, like learning the kernel. And same for the two PDE methods at the bottom. So you see we are able to reconstruct the temperature profile globally as well. So we also looked at the problem of learning partially observed dynamical systems where some of the states are not observed and others are observed. And then this also, so all we had to do is just to modify the criterion. And then this also worked well for Lorentz. We had also to increase the number of parameters, so about 22 parameters that we see here, to take into account the fact that we are dealing with a slightly more complex system, but also with variables that are not observed. And so these are the results for this case. So the states and the errors. So this is the reconstruction of the attractor from data. And then you see now the natural question is that how do you find the base kernel? So in a way, so here the way we approach it is that was more of a bottom to top approach where we try to find the simplest kernel from the beginning by looking at different toy models and then summing up the kernels that are giving the good performance for different toy models. Here we are going to do it the other way around, where we start with the kernel of the following form, which is the sum of different elements, like m elements. And we call this method like sparse kernel flows because we are implementing a sparsification constraint. So here, this is like our classical relative error, but this will change depending on the objective. So the key here is that we are just like sparsifying the coefficients where some of the thetas will be set to 0 if they are underneath certain threshold. And the other objective here is that we wanted to apply this to a large database of dynamical systems. So we look at a database of here it says 131, but it became like later on like 135. So we applied it to a database of 135 dynamical systems at once, like developed by William Gilpin. So it's like different dynamical systems from different applications, with physics or chemistry or electronics, etc. So our goal was to find a large kernel so that if you apply it to the database, then you are going to get good results. And so that kernel is this one. It's like about 40 parameters. I said the idea here is to try to detect patterns. I mean, the key here, so there's always like this debate in learning dynamical systems. Should we learn the dynamical system or try to learn the patterns? So here I'm mostly pushing for the learning of the patterns. And in a way, so these are kernels that are meant to learn the patterns of the dynamics. And then we let the data decide about which elemental kernels to keep and which ones to remove. And then this worked well for this large database. So these are examples for example, in chemistry. So you got this dynamical system, and this like the attractor from the right-hand side is without with learning the kernel. This one is without learning the kernel. And then this one, like electronics case, so we got this attractor after and before. And then here, for example, for these two examples, we computed, so we get like 15 parameters, and some of them, as you see here, were set to 0 because they are underneath a certain threshold. For multi-Chua, there's one parameter that was set to 0. You see, I mean, this made a huge difference in terms of performance because we looked at two metrics. One is the SMAP, which is the short-term predictions, and the Hausdorff distance is for the long-term behavior, where we are trying to reconstruct attractors from that. And then you see this made like a good impact on the performance. And then, yeah, I said by changing the first term, we can move from different objectives. Yeah, question? Yeah. Yeah, so this one, as I said, it's more, I mean, the idea was that the way I thought about it at the time was that, yeah, so what are we trying to do when we learn dynamical systems? As I said, the goal is not necessarily to learn the right-hand side of the dynamical system, it's to learn the qualitative behavior. And so I thought, okay, so what are the main toy models in dynamical system theory that exhibit the prototypical behaviors in dynamics? So I went to different toy models, one by one, like the logistic map, I mean, the Henon map, the Bernoulli map, Lorentz, and so forth. Probably like maybe about 10 toy models. And I was just trying to crack them one by one, try to find the simplest kernel for each of them. And then once I found these, then I just said, okay, let me just see if there is a way to learn more complex dynamical system by just summing them up. So this is what this is about. It's really doing the sum of elemental kernels that are used for learning prototypical dynamical system. Yeah, so this is basically, but you see, I mean, here the idea is you have this kernel, some of these kernels, I mean, they are about like short term, others are about like locally periodic or other behavior, other ones are about globally periodic behavior. So for example, this one is about locally periodic behavior. This is about like globally periodic, exponential minus sine square. So this one was like making it local through the Gaussian. So these ones with the maps are triangular kernels for the discontinuities and so forth. Yeah, but I said it's more of exactly, that's the idea. Exactly, the idea is, as I said, is not necessarily like you have you are developing a Taylor series and automatically you are trying to learn the best the best monomials the best Taylor series expansion. Now here it's like more of find it like the templates in terms of qualitative behavior and then doing it backwards. Yeah. And so that's the second one. I mean, that we said is developed. It's we call the Hausdorff metric kernel flows, where we change the objective, right? I mean, as I said, when you learn dynamics, you have to keep in mind what is your objective. Do you want to learn short-term behavior or long-term behavior, or you want to keep the statistical behavior? So here we said, okay, let's assume that now we want to focus on reconstructing attractors. So therefore, we change the term. So before, for the like regular sparse kernel flows, I mean, the first term was wait, so here. Yeah, the first term was that one. As that, if I remember, it was the relative error that was close to short-term behavior. Now, if we change the first term and we say, okay, now our objective is to learn the long-term behavior, especially in terms of attractor reconstruction, then we are going to change the first term. And then but still the same spirit of sparsification is here through the L1 norm and the theta, and we applied it on the same data set. And then we compared between different versions of kernel flows, regular kernel flows, sparse kernel flows, Hausdorff distance regular kernel flows. And so basically the regular means without sparsification. So we set lambda is equal to 0. And then the sparse is about sparsification, whether sparsification in for the short term or the sparsification for the Hausdorff distance. And we looked at the 135 systems. Here are just illustrating what happens to these 5 systems. But statistically, I mean, this is what happened, is that if you look at the short term, then statistically, Hausdorff sparse kernel flows is the best. But it's statistically, because we may have some examples where other versions of kernel flows are doing better, but we notice that statistically, Hausdorff distance sparse kernel flows is doing better on the short term, is also doing better in the long term. So in a way, if you want to keep, in a way to reinforce the message that if you want to learn the dynamical system, it's better to learn the qualitative behavior, in which case you have to try to find a good approximation that approximates the attractor, because the attractor is characterizing good characterization of the qualitative behavior of the dynamics. So, and this is something we could see, as I say, it's like more of a numerical argument where we took like 135 system, and we said, yeah, this not necessarily 33, it became like 35 later on, where we show that, yeah, by using a metric that encodes qualitative behavior, then we are doing both, we're achieving both objectives, whether it's short-term and long-term. So do you have like 10 minutes left? Or? Okay, yeah. So, okay, now as I said, here we want to move, so instead from learning the dynamics to developing a database theory of dynamical systems without necessarily learning the dynamics. So we are going to move to like to few other things, which like, for example, detection of critical transitions for multi-scale systems. So for example, I'm just going to go, as I said, I'm trying to have a survey. So here we want to consider slow fast SDE. So we've got like a stochastic differential equation with critical transitions. And then, for example, stochastic von der Pol that is known to have critical transitions. And then we proved that the MMD, the maximum mean discrepancy, actually achieves its maximum at the critical points from the dynamic perspective. So basically here, the way we computed it, we just took a sliding window, and then we divided it into half, and then we computed the MMD between the first part and the second part of the sliding window, and then we slide it, and then we proved that the MMD is a good metric to detect critical transitions in stochastic differential equations. So at least in this class of slow fast dynamics. So it comes back to the idea that, yeah, you don't necessarily have to learn dynamics. You can always try to find database versions of existing things. And here it was like using a database metric to show that you can detect critical transitions in slow fast SDEs. There's another approach here, which is also about like learning kernels that encode the critical transitions. So we also like built like kernels, like we call them like local kernels or like baby kernels that are like very small in time scale, and then you integrate them to be able to detect change points. So we got inspired by this Gabor wavelet to construct kernels in different in space and time, and so that would be the kernel that the expression of the kernel that we integrate. We don't necessarily have a closed form expression, but at least it's built from data. For example, if you take the stochastic von der Pol, then you are going to see, for example, that the new kernel that we built using our method is that one. As I said, it's not necessarily something you know its expression, but at least you know that it has this triple integral form. And you see it's detecting well the critical transitions. So this is a good illustration of the approach. And then this is for example, the illustration, the signal versus the reconstruction, and then also learn the noise, because when you are learning random dynamical systems, the noise is integrated in a dynamic way. So it makes sense actually to also learn the intrinsic noise versus measurement noise. So here we also try to learn the noise that is something that is intrinsic, that is intrinsically characterizing the system. And then in order to look at different modes, I mean, we also define this energy of the sliding window. In a way, we try to find like another metric, the database metric that allows us to characterize change points, whether for detection or prediction. And then, so we got that quantity here. And you could see that, for example, for the case of this slow fast random dynamical systems, and we got that our energy here, by playing all certain parameters, you get detection. And then on playing all the parameters, you could see that you are able to extract an early warning signal by just looking at the slope here. So by looking, for example, alpha is equal to 0.1, which is one of the parameters of the kernel, then you can won't really be able to make predictions. And then, but if you don't design it well, then you are going to miss different change points. So the other theory that we looked at is the center manifold theory, a center manifold theorem. So where our goal here is to analyze the stability of the system. So here we are trying to find a theorem that, given your data, you are able to decide whether the origin is stable or not. So it's not about necessarily always learning the dynamical system. We are also trying to find to learn qualitative properties. So here it's about stability. So center manifold theorem is telling us that if you have a system who some of the eigenvalues are on the imaginary axis and others are on the left open left half plane, then you can infer stability properties from the ones on the imaginary axis. So like intuitively, for example, if you have this dynamical system x dot equal to f of x, take the linearization, then if some of the eigenvalues of f are positive, then you can infer that the system is unstable. If all of them are negative, then you can infer that the origin is stable. But if some of them are on the imaginary axis and other are on the open left half plane, then this is where the center manifold theorem comes in. And then intuitively, yeah, you guess that everything will depend on the x1 part. And this is what the center manifold theorem is about. And the way you construct this reduced order model is by solving this PDE here. And yeah, so the approach here is to solve this PDE using kernel methods. And so this is our contributions, that we construct the center manifold directly from data, and then we have also a database version of the center manifold theorem itself. So these are like different technicalities. That's an example of a system where we can apply the center manifold theorem. So this is the center manifold. This is y is equal to minus x squared. And this is what we got with different approximation true. So you see, it's very close to the true center manifold for different kernels, K1 and K2. It is for a 2D model where you have center manifold is of dimension 2 for this 3-dimensional system. So y does go to minus y, eventually go quickly to the origin, so it will not contribute to the stability properties. And this is how the center manifold looks like for different kernels. Then construction of Lyapunov functions. We're also looking for stability properties for like a larger class of dynamical systems, where here the way we dealt with is that if you have x dot equal to f of x, so the way we are going to do it is that we approximate f from x, and then we construct Lyapunov function v hat for phi hat for f hat, and then we prove that v hat is also Lyapunov function for the original system x dot is equal to f of x. So these are essentially, in a way, they play the role of energy for nonlinear dynamics. And so here we'll say that Lyapunov function is just a function that decreases along the solutions of the differential equation. So basically, its orbital derivative is negative. And in a way, this is what will help having a database version, because the goal is to reformulate this differential inequality as a PDE. So this is, for example, what Peter Giesel and Van Land show, that you don't necessarily have to solve the differential inequality. You can solve this PDE by setting the right-hand side to a negative term, for example, minus norm of x squared. It can be a function minus px where p is positive. And so, yeah, so what Giesel showed was that if you now f x dot equal to f of x, and it has like an equilibrium point with certain stability properties, then for given a certain condition, you can always construct Lyapunov function, and then you can prove that it's Lyapunov function for the original system with the differential inequality. And so that's the ansatz for the V. And then here is also that the coefficients themselves, they satisfy a system of linear equations. And yeah, so here I have the decrease in the orbital derivative of the true versus approximation. And so what we did is we extended this work to the case where you don't know the dynamics, and then we showed that similar results are still valid. For example, for this system here, we know the true Lyapunov function, x1 squared plus x2 squared, and then we assume that we don't know the right-hand side, we have data only, and then we showed, that this is an experiment for Lyapunov function. When you increase the number of data points, you are converging to the quadratic function. Same thing for error, the orbital derivative is negative when you increase the number of data points. The last thing I think I will have time to do with this is how to solve the Hamilton-Jacobi-Bellman equation. So in that case, it's like a nonlinear PDE. So it's generally intractable to solve. And the way we are going to tackle it is that we are going to convexify the problem. So by mapping the Hamilton-Jacobi-Bellman equation into using our Schur's complement, we are transforming the SJB into a linear matrix inequality, which makes the problem convex. So it's like about convexification here. Remember, the question is 5 minutes. Yeah. So here the question is, remember the story was we map a problem to a different space where the computation becomes simpler. So here the key is simplification means convexification in this context. And so here we are transforming SJB into a linear matrix inequality. So we are adding different constraints to this linear matrix inequality in the Hilbert space. But this makes us this gives us like the following results for free. Or I say it will become a convex optimization problem. There will be theoretical guarantees, and then we get good performance for different cases. So that's, for example, if we have this optimal control problem, this is the cost functional. I mean, this is the optimal feedback control. This is like in principle, if you manage to get the V star. So there's a lot of work that has been done, whether analytically or using neural networks about this kind of techniques. But I mean, here our contribution is somewhere, as I said, the advantage of kernel methods that they are somewhere between theory and purely database. So basically, you are having theoretical guarantees for a database approach. So in that case, what we are going to do is that we are going to transform the HJB inequality into a linear matrix inequality with the following reformulation using like Schur complement. So in that case, we are going to assume the following ansatz for the gradient. And so in that case, the LMI constraints, the SJB becomes like linear constraints on these coefficients Pi. So it reduces the infinite dimensional problem to finite dimensions. The P coefficients P become optimization variables, so like an optimization problem over the P's, and the P's themselves, they satisfy a set of linear inequalities. So we moved from linear set of equations to still linear, but in that case, it will be inequalities. One of the issues here in HJB, and like anyone who worked on numerical methods for solving PDEs, is how to avoid the trivial solutions. And the way we dealt with it is that we want to always come back to the linear case. So remember, the story is that we map to a higher dimensional space where computations become simpler. But then you see we still want to fall on our feet when we have a trivial problem. So here we want to make sure that when we have a linear system, then we recover things that we already know. And here, so we want to recover Hamilton's the Riccati equation in the linear setting. So we have the following constraints: b of 0 is equal to 0, gradient is 0, and then the Hessian satisfies the Riccati equation that is given by the following equation. So yeah, so this is the advantage, is that so we get consistency with linear systems when the system is linear. Consistency with linear theory when the system is linear, and then we are avoiding the trivial solution because we can always find local estimates. So this is what the convexified problem in the Hilbert space becomes. So which is the optimization problem on the P with the following constraints. And these are things that people working with optimization solvers can implement very easily. So we got also like theoretical guarantees, convergence rates for the gradient. So they are, for example, the 1D system. So we managed to get like a good estimates. So these are the errors. So all trajectories for different initial conditions converge to the origin. These are the plots for 1D, 2D, same thing, like similar conclusions. 3D van der Pol, sorry, 2D van der Pol with control. Yeah, are we done? Yeah, sorry. So okay, so now we are going to wrap up. So yeah, so basically here the same spirit applies for SJB. And yeah, so this is the summary of the approach. So that we managed to transform nonlinear SJB into linear matrix inequality via show complement, which allows for complexification. So this also gave us theoretical guarantees and good numerical results. Yeah, so let me just conclude. Oops. Yeah, okay, yeah, so here we showed different variants of kernel flows to approximate chaotic systems. We talked about MMD and external kernel decomposition to detect critical transitions. So then I didn't talk about this part, but at least I showed other parts where you have database theory of dynamics through detecting critical transitions, center manifold, and Lyapunov equations, and also SJB. So the preprints are all online, Archive, ResearchGate, and some of them, or many of them actually were published. So we have a special issue on machine learning dynamics that you are welcome to submit to. So we have a seminar, machine learning and dynamical systems seminar that you can join the mailing list on my website. And yeah, so I'm happy to take questions and collaborate with you if you want, if you have a question. All right, thank you.